Hello, and welcome to this presentation on deriving optimal multiplication by constant circuits with a SAT-based constraint engine. It's a joint work with my colleague Amit Metodi. Amit and I, we both work for a company called Cadence Design Systems, or Cadence for short. It's one of the major providers of tools for electronic design automation, and currently I think it employs about 15,000 people and has a headquarters in California. So at Cadence, we make software used by engineers in all stages of design and verification of their microelectronics. So I'd like to start by giving you some context on what we do. Let me explain the basic idea of functional random-based verification. Assume I'm designing a new piece of electronic hardware, which can be really anything, can be a processor, a sensor, storage. So here's my design, and I'm showing some schematics here, but in reality, it's not schematics. It's a description which look more or less like code in a programming language, in a special kind of programming language for designing hardware. And obviously, I need to verify the functionality of my design, and I need to do it long before the design makes it to silicon, because having bugs in silicon is way too expensive and I cannot afford that. So I need some tools to verify it at the level of design, and I need some tools for the job, and Cadence makes such tools. So first thing I need is a simulator, and the simulator can simulate the behavior of my design at the level of gates, registers, etc. I need checkers to look at the results of the simulation and see if they make sense. I would probably use coverage to keep track of how much testing I've done so far and what interesting cases I covered or not. And finally, I need a generator of inputs to drive into my simulation. I need to send in some data that makes sense for my hardware design. And now it's a de facto standard in the industry to use constraint models for defining test data and use constraint solvers which generate random solutions and use those random solutions, drive into the simulation, etc., etc. So that's the part I work on, and it's the randomization engine. To give you some idea of randomized test generation, let us consider this trivial example. This language is called System Verilog. It's standard in the electronic design and verification world, and we use its subset here, which is a constraint modeling language. Don't worry about the syntax, the basic ideas are really simple. We try to build a sequence of CPU instructions for our primitive CPU with 8 possible opcodes. Here you can see them at the top. We define an instruction as a class. Each instruction has an opcode and an 8-bit argument. We define a program as a sequence of instructions, and we constrain our sequence. Here, we only require two things. First thing is that the last instruction in the sequence must be a stop instruction. And the second thing we require is that the argument of any jump instruction should be within the sequence. So we would jump within the boundaries of the program to some other instruction. So it's all really simple. We call randomize, which has an effect of handing our model to the randomization engine, and the randomization engine may produce a program that looks like that. And as you can see, the last instruction in this program is stop instruction, and the arguments of all the jumps in the program point to valid locations in this program. I wish I could spend more time talking about random test generation, but that is not our topic today. Let me just make a point that our randomized generator is good not only for test generation. It's a general purpose platform with a modeling language and powerful solvers. So this talk is not about test generation, it's about a constraint problem which we solved with our tool and actually improved the state of the art. Let me now introduce the problem this talk is actually about. And the problem is we want to build an optimal circuit for multiplication by a given constant and it should be optimal in the sense that we use as few adders and subtractors as possible. Here, for example, we are trying to construct a circuit which multiplies any input by the constant 85. So first thing we can try is to apply the textbook algorithm based on shift and plus. And as we can easily see, 85 is this 0, 1, 0, 1, 0, 1, 0, 1 in binary. So the multiplication by 85 would be x shifted by 6 positions plus x shifted by 4 plus x shifted by 2 plus x. The question is, can we do better than 3 adders? And of course we can, otherwise I wouldn't be asking. So let me show you the circuit that does the same job and is using only 2 adders. And the idea here is quite simple. 85 is 17 times 5. And multiplying by 17 is kind of easy. We can multiply by 16 and add x once again. So multiplication by 17 is x shifted by 4 plus x. That's the first part of our circuit. And for the second part of our circuit, we multiply the result by 5. And the principle is the same again. We shift the input by 2 positions, multiplying by 4, and add the input again, multiplying by 5. And here we got a circuit for multiplying by 85, which is only using 2 adders. And before I show you the model and our solution, let me say a few words why I think it's actually a very interesting problem to solve. First of all, it has some very useful and important applications in the domain of synthesis, such as digital filters, DSP applications. Second point, it's a hard problem, so it's a good benchmark for any constraint solver. And in fact, this whole research, this whole work started as a benchmark. I modeled this problem for our solver because I wanted to benchmark our solver, and that's how it went. So, like I said, it's a hard problem. The general complexity of finding optimal circuit is still an open problem. And it's hard to find optimal circuits for large numbers. So it was easy with 85, but take a larger number like this 3243, and it's not so trivial. There's also a conjecture that 7 adders or subtractors should be enough for all 32-bit multiplications. And it was interesting to play with that too. We also did some experiments in proving optimality of our results, and I'll say a few words about that in the rest of the talk. And this problem is hot. There's been a lot of research done in the last 2 decades using various techniques like graph reduction, playing with encoding, heuristic, and more recently linear programming. So it was interesting to see if we can contribute something. And now it's time for me to show you our constraint model. I'm not going to explain it in any level of details. The workshop paper explains it quite well, so please read the paper. It's only 6 pages long. And for the purpose of this talk, I'd like to make a few points about this model. My first point, it solves the problem. Well, it is important. If you load this model into the Cadence simulator, you can get a solution for a specific constant k, and with a given number of adders or subtractors, and those are 2 constants in this model. So it works. My second point, it fits on the slide. I mean, that's about as much code it takes to solve this hard and interesting problem, which is a good illustration to the power of the modeling language and the tool. My third point, it uses the unmodified randomization engine, so we didn't need to do anything special just to model this problem and run it. And finally, it improves state of the art, as we would see in the next few slides. Let me show you some examples of what we can do with our model. Let's find an optimal multiplication for the constant 3243, which we mentioned earlier. Running our model for that constant, and with the limit of 4 adders and subtractors, we can find a solution that you can see here on the slide. You can see how it works. We build some temporary results. We build T1 from the input, then we build T2 based on the input and T1, then we build some T3 based on T1 and T2, and finally we build the input of the multiplication circuit based on T3 and T2. You are welcome to check the math. It all works fine. Now, how do we know it's an optimal multiplier? We can actually prove it. We can try to find a multiplier for the same constant in 3 nodes, and we get a contradiction from our solver. The solver proves there's no solution to that, and all it takes is less than 1 second. So we know our 4-node multiplication circuit is in fact the minimum size circuit possible for that specific constant. And for our next experiment, we confirmed some interesting capacity limits of optimal multiplication circuits. Look at the limit column of the table that you can see on the slide. The meaning of the limit 11 is that we can do all multiplications by numbers from 1 to 10 using only one adder or subtractor. Try it, it's a very easy exercise. 11 is the first number where we need 2 adders. Similarly, any multiplication by a constant less than 43 can be done in 2 or 1 adder or subtractor. 43 is the first number that requires 3 nodes in the multiplication circuit. 683 is the first time where we need 4 nodes, and so on. The limit for 6 was a conjecture. The number was reported in the literature, but there was no proof it cannot be implemented in 6-node multiplication circuit. We proved it using our model. We were running a parallel SAT solver with 20 threads, and it took us about 7 hours of parallel processing, or about 6 days of equivalent linear time. So that's the first time that limit is established as a number that requires at least a 7-node circuit for multiplication, and that is our contribution to the state of the art. The time of this video is strictly limited, so unfortunately I cannot go into any additional details. So please, if you are interested, if you have comments or questions, please contact me directly via the conference web portal or through my email shown on this slide. And with that, I'd like to stop and thank the organizers and thank the audience for watching this video. Thank you.